So it basically asks us use the linear congruential method to generate a sequence of random numbers with these settings of the parameters, where the seed is 27, multiplied is 17, increment is 43, and the modulo is 100. Now, we have already generated the first integers in our presentation file. Now we are going to practice it with Excel. First, we can write these 4 parameters here, and my seed is going to be equal to the seed cell here. And the next thing will be written in this form. So let me show what is written here. I'm just going to calculate multiplier cell times the previous integer plus the increment, and I'm just going to calculate the mod of this with respect to modulo 100. And this function mod will be able to do that. Now I need to put a $sign in front of the letters and the numbers for each cell here, because when I propagate this to down, I would not like to change these parameters. Okay, so as in each calculation the previous integer will be used, but in each calculation always these fixed 3 values will be used. And you see this sequence is regenerating itself with this setting. So if you check this value 1 and this value 1 at the 21st index. So the first index is regenerated at 21st index, and in this setting, the period of the sequence is 20. Now we are going to convert these integers generated by the linear congruential method to random numbers. And how can we do that? By dividing each integer to the modulo. Again, we are fixing the modulus value here, and every integer is going to be divided to the modulo here, and we are going to convert these integers, which are distributed between 0 and n-1, to rational numbers between 0 and 1. Now, of course, this is a very, very weak choice of the parameters in the linear congruential method. Now, in the next practice, we are just going to play around by trial and error, and we are just going to choose different seeds, different modulo, different increment values, and different multipliers. And we are going to see, even with the choice of the seed, by changing the choice of the seed, you can practically change the period of your sequence. So if you choose your seed as 1, the period will be 16. But if you choose your seed as 2, the period will be 8. And depending on your choice, if it is even or an odd number, then the period is going to be affected from that. In fact, you can try different modulo. I mean, I'm changing the modulo to, let's just say 199. And in that case, you are going to get a different sequence here, and you can check the period of this sequence after how many integers you are going to repeat the same integer again. I think this is a better choice. Remember, this modulus operator should be very, very large. Okay, so here we are trying to test the suggestions of the Lewis. The multiplier and the modulo are selected like their suggestion. So this is 2 to the power 31 minus 1, as you can see here. And this is the seed. And according to the previous linear congruential equation that we have mentioned, we are basically generating the integers that are supposed to be generated by this linear congruential equation. And no matter how long you generate, okay, this is just going to continue for a very, very, very long time, my friends. In fact, in this practice, I am generating 10,000 integers. No previously generated integer will be repeated. In fact, with your computer and with the size of your Excel file, it would be impossible to practice the regeneration of the first integer generated here. Now, the random numbers are obtained by dividing each integer to the m value here, but you can also obtain them by dividing to m plus 1, if you remember. If you divide it to m plus 1, it is just going to be much easier for the computer, but it doesn't matter which one you choose. I mean, whether m or m plus 1, after all, it is just going to, the numbers, the digits are going to be approximately the same. So even if I change this value to +1, what you are going to see is practically the same number. And if I double click on this and if I propagate this down, again, all values are going to be the same. However, if you choose n+1, remember the division to a number which is in the form of a multiple of 2 is just going to be performed easier by your computer. I mean, you wouldn't understand the difference, but I mean, for the sake of your computer, you can divide it to n+1. Not for 10,000 numbers, baby, but if you are going to generate a very long sequence of random numbers, you can measure the time difference between the choices of the denominator in this division operation. Now, finally, we are just going to draw a histogram of the random numbers that we have generated. Now, let's just say these are the random numbers that are generated, and let's just say you are writing your student number here, okay? So this is just going to be the seed, and with this seed you are going to, if you write your student ID here, so let's just say my student ID is 1, 2, 3, 4, 5, 6, 7. Now you are going to get your own random number sequence with that, okay? And in fact, it is totally different than anything else. Let's just change the seed to 1, 2, 3, 4, 5, 9. So you are getting totally different, okay? So even with a small change in the seed, you are just going to get a different beginning in your sequence, okay? Now, this is a very long sequence in theory because there are too many integers here. By changing the seed, you are starting from a different integer in this sequence, okay? And that is most probably very far from another student is starting. So with respect to the choice of your seed, you are always going to get a different random number sequence, which is statistically independent from the previous one. Now, you may ask this question, how this is statistically independent? I mean, every next random number that is generated by this algorithm is dependent on the previous one. Now, we are talking about the statistical independence, okay? I'm not indicating they are independent. This is therefore they are pseudo-random numbers. Pseudo-random numbers conform to the property of statistical independence. Now, my friends, if I just cover these 4 values, now by looking at these random numbers, I am asking you, can you see the dependence? Can you discover the dependence between these random numbers? How they are dependent? It is impossible for you to identify. I mean, no matter how long this sequence is given to you, you will never ever be able to guess or calculate these values in the equation, unfortunately. Therefore, these pseudo-random numbers are actually imitating the properties of philosophically mentioned random numbers. They are statistically independent. However, they are not actually independent. So what is necessary is the statistical independence. Now, if you draw the histogram of these random numbers, which are 10,000 random numbers, if you draw the histogram of them, you are basically counting the number of random numbers observed in each of these intervals. You are going to see the histogram of the sequence by these frequencies. So it says, for these 10,000 random numbers, 335 of them are observed between 0 and 0.0333. 329 of them are observed in the next equidistant interval, so and so forth. So you see the observed frequencies in each subinterval are approximately similar to each other. And if you draw a plot diagram of the observed frequencies within each interval, you will see that these random numbers are imitating the property of uniformity.